This is Dr. Mahesh Kalyan Shetty, Associate Professor, Department of Civil Engineering, Walchand Institute of Technology, Solapur. Today we will discuss about analysis of indeterminate structure by moment distribution method, where we will focus on only introduction. As it is covered in the earlier sessions, we have many methods for the analysis of indeterminate structures. And we also aware that there are basically two approaches of indeterminate structural analysis. One is called as force method of analysis and another is displacement method of analysis. In the force method of analysis, we have these many methods, whereas in the displacement method, we have these methods. Out of these, today we'll focus on moment distribution method, which is the very easy and simplest method among all. So therefore, from this discussion, we may say that the moment distribution method is one of the method of displacement method of structural analysis. Moment distribution method was first introduced by Professor Hardy Cross of Illinois University in 1930. Earlier, people used to struggle when to solve such kind of complex kind of problem with the available methods at that time. However, after the introduction of this moment distribution method, the analysis became easy, and since this moment distribution method is very simple and quick, therefore it becomes very popular after 1930. This method provides a convenient means of analyzing statically indeterminate beams and rigid frames. So we can analyze beams as well as rigid frames. And the most importantly, it was used when number of redundants are large and when other methods becomes very tedious. So as I told already, that when we have large number of redundants, then other methods becomes very tedious. However, moment distribution method is very simple in that case. Therefore, it is very popularly used on the. Now we'll look at some important terms which are used in this topic, such as stiffness. So stiffness is nothing but it's a moment required to produce a unit rotation or slope at a simply supported end of a member, and it is denoted by symbol K. Now we have two cases for this stiffnesses. Usually in case of the beams, we have these two cases. One is the when both ends are hinged, and another is when one end is hinged and other end is fixed. So let us discuss these two cases and we'll see how the stiffnesses of the members is to be determined. Say the first one is beam hinged at both the ends. So this is how we can look at this. A and B both are hinged, and the moment required to produce a rotation, unit rotation at A is called as stiffness, and opposite end or the far end is hinged. In that case, we can have this value as 3EI by L. So from the structural analysis concepts, we can derive, especially the slope deflection method we can apply here, and we can derive this equation. So the moment required to produce unit rotation is 3EI by L. Therefore, we call this 3EI by L as the stiffness of this particular member, which is denoted by K. Whereas the second case, beam hinged at near end and fixed at far end. So this is how we get this problem, where you can see the B is now fixed, and for this case, if I apply the moment to produce a unit rotation here, then that moment required will be equal to 4EI by L. So therefore, again 4EI by L, we call it as a stiffness of this particular member. Therefore, we have two cases, as I told. The first case is when the opposite end is hinged, stiffness is 3EI by L, and when the opposite end is fixed, stiffness is 4EI by L. So this is how we remember these values, and we will use further when we solve the problems. Later on, let us go for the another term, carryover factor. So whenever the moment is applied to one end, some fraction of the moment is transferred to the opposite end, such as, so a moment applied at the near end induces a fixed far end moment equal to half its magnitude in the same direction. So that we can see here in this particular problem, when I apply the moment here, half the moment is transferred to the opposite end. You can see half m. And if the opposite end is fixed, then only this transfer takes place. Otherwise, this transfer doesn't take place. And this we call it as carryover factor. So carryover factor is half now. Whereas in the second case, if I look at the opposite end is a pin or hinge, therefore no moment is transferred here. Therefore, the carryover factor for this case is 0. So this is how we take the meaning of carryover factor. So it depends upon the opposite end. If the opposite end is fixed, it is half. If opposite end is pin, it is equal to 0. So I request you to take a pause and answer these MCQ questions. First one is moment distribution method is invented by. So 4 scientist names are given. You have to identify the correct one. The second one, the carryover factor in a prismatic beam whose far end is hinged is. So 4 values are given. So just think over it, take a pause, answer these questions and resume the video. Welcome back. So this is the first question. Moment distribution method is invented by Hardy-Cross, as it has been discussed already in the earlier slides. And the second question, carryover factor in a prismatic beam whose far end is hinged. So if the far end is hinged, no carryover is possible. Therefore, it is 0. Let us continue with the another very important concept in this method, that is called distribution factor. So whenever we apply a moment to any of the joint, then the member is transferred to the moment is transferred to different members as per their distribution factor. So the factor by which the applied moment is distributed to the member is known as the distribution factor. So this we'll discuss with the help of one small case here. So suppose 4 members are meeting at one particular joint, and these members have got different support conditions. So member 1, member 2, member 3 and member 4. And if this joint is subjected to a moment m, so you can see some fraction of the moment m is transferred to the member 1, some fraction of the m is transferred to second member, third member and fourth member. That we'll discuss how to find it. Now first of all, we have to find the stiffness of the joint. So stiffness of the joint is nothing but it is a summation of stiffnesses of all the members which are meeting at that point. So therefore we have 4 members meeting at this joint, therefore stiffness of all the 4 members we have to add so that we get a stiffness of the joint. Then first member, stiffness of the first member, as we know that there is a hinge end, far end is hinged, therefore it is 3 EI by L. The second member, far end is fixed, therefore it is 4 EI by L. Third member, far end is hinged, therefore again 3 EI by L. And fourth member, far end is fixed, therefore it is 4 EI by L. In this way, we can calculate the stiffnesses of all these members independently. And you can take a summation of all these, you will get total stiffness of the joint. Now the distribution factor is nothing but it is the ratio of the stiffness of the member divided by stiffness of the joint. So if I consider the first member here, the distribution factor for the first member df1 is equal to stiffness of member number 1 divided by stiffness of joint. So K1 upon K. In the same way, M2 is, distribution factor for second member is K2 upon K. Distribution factor for third member is K3 upon K. Distribution factor for fourth member is K4 upon K. In this way, we can find out the distribution factors. And once we get the distribution factors, we can find out the moment transfer to these members, such as say first member, moment transferred is M1. So M1 will be equal to distribution factor for the first member multiplied by M. It means some fraction of this M is transferred to M1, and that fraction we call it as distribution factor. In the same way, M2, M3 and M4, all these will just continue with the same logic. And one more thing, that all the distribution factors naturally have to be in fraction, and summation of all the distribution factors shall be equal to always 1. So that we have to take care and accordingly we have to find the distribution factors. So in the while we discuss the numerical examples, there we'll learn in detail how the distribution factors are to be determined. These are some sign conventions which we follow in this topic, such as the support moments. So moments, we take this sign convention. Clockwise moment we consider positive, anti-clockwise moment we consider negative. Same with the rotations also, that is slope. Clockwise slope we consider positive, anti-clockwise we consider negative. Whereas in the settlements, sinking of the support, because many times we come across with the sinking of the supports, so there we consider this sign convention. The settlement will be taken as positive if it rotates the beam as a whole in clockwise direction, whereas the settlement will be taken as negative if it rotates the beam as a whole in anti-clockwise direction. So these are some fixed end moments for the beams. So these are all fixed end moments we need when we solve the problems. Some typical cases are presented here. Say simply the fixed beam subjected to UDL. So fixed end moments is QL square by 12 if the intensity of load is Q. If it's a point load at the center, so these are the fixed end moments. If suppose there is a eccentric point load, then these are the fixed end moments. If there is a triangular load, these are the fixed end moments. If suppose a couple is present in between the span, then these are the fixed end moments with the directions that you can consider. These are the references which are used for this presentation. Thank you. Thank you very much.